Welcome to the first guided exercise of the course. The guided exercises have been developed to give you an idea of how to work with the key concepts, formulas, and equations introduced in the course. You will be presented with a sequence of interactive tasks, each of which requires you to provide a solution. In this exercise, there are 6 tasks, and you will be asked in each case to select the correct solution to a particular problem. The first task is also designed to help you learn how to use the interactive environment and should be somewhat easier than the later tasks. As you make progress, you will be working with less guidance. You will have to recall which formulas to use for specific tasks and think about how to rearrange them where necessary. Regardless of whether you provide a correct or incorrect solution, you will receive feedback that will help you identify your stronger and weaker areas. Providing the correct solution will unlock the next step in the sequence, but the real goal is to develop your ability to respond to real-world problems by learning to skillfully apply your theoretical knowledge. This particular guided exercise is about polytropic processes. Understanding polytropic processes is important if you want to understand the thermodynamics of hydrogen systems, particularly when there is a need to calculate an input or output, whether pressure, volume, or work done. One of the examples we will look at here is hydrogen compression in a tank storage system. But the polytropic process is also relevant to other kinds of systems, such as pipeline networks or expansion machines, for example. You've already learned something about how thermodynamic processes in relation to the behavior of hydrogen, including isothermal and adiabatic transformations. You've also seen how real-world systems like compressors and expanders operate in environments where both heat and work interactions influence the behavior of the system, something which we can understand better if we understand the polytropic process. By the end of this exercise, you will be able to understand the significance of the polytropic exponent N in thermodynamic processes. Apply this understanding to real-world scenarios with a focus on hydrogen compression. Calculate key parameters, including pressure, volume, and work done, using the polytropic equation. Let's get started by reviewing the key concepts before we move on to practical calculations. The polytropic process is a thermodynamic transformation that can model a wide range of processes by adjusting the polytropic exponent N. The process is described by this equation, where P is the pressure, V is the volume, N is the polytropic exponent, which determines the nature of the process. C is the constant. Different values of N can be used. N equals 1, isothermal process. Temperature remains constant. N is equal to gamma. Adiabatic process, no heat exchange with surroundings. N equals 0. Isobaric process. Pressure remains constant. N is equal to infinity. Isochoric process. Volume remains constant. By adjusting N, we can model real-world processes more accurately than if we assume purely isothermal or adiabatic conditions. This is especially important in hydrogen systems, where compression and expansion occur under conditions influenced by heat transfer and work interactions. In the next task, you will have to answer the following question. Which equation correctly represents the polytropic process? In real-world machinery, such as compressors and expanders, the polytropic process offers a more accurate depiction of operations than is possible with simpler models. Compressors, for example, are used to increase the pressure of gases like hydrogen, often for fuel cell or storage applications. Once again, compressors do not operate in isolation but are influenced by heat transfer from the environment and work done on or by the system, measured in joules. Using a polytropic approach, we can model how a hydrogen compression system behaves under non-ideal conditions. Let's consider a hydrogen compressor that compresses hydrogen from a lower to a higher pressure under polytropic conditions. The initial conditions are as follows. Initial pressure, P1 is equal to 5 bar. Initial volume, V1 is equal to 1 cubic meter. Final volume, V2 equals 0.5 cubic meters. Polytropic exponent, N is equal to 1.3. We choose N equals 1.3 because heat exchange is neither negligible nor fully adiabatic. Our objectives are to calculate the final pressure P2 and the work done, W, during compression. As we know, the polytropic equation, PVN equals constant, allows us to calculate the final pressure. We start with P1 multiplied by V1 to the power of N is equal to P2 multiplied by V2 to the power of N. Rearrange the equation to solve for P2. P2 is equal to P1 multiplied by V1 divided by V2 to the power of N. Now, we can substitute the known values into the equation. P2 equals 5 multiplied by 1 over 0.5 to the power of 1.3. We can then perform the calculation to find the final pressure P2. Now we can move on to the interactive task. The question will be, what is the value of P2 from the given options? Step 2. Calculate the work done during compression. The work done during a polytropic process can be calculated using the following equation. W equals P2 by V2 minus P1 by V1 to the power of N minus 1. Because you've already calculated the final pressure, P2, you can substitute it into the work equation along with the other known values. You now have to answer a couple of questions. The first question will be, how much work did the compressor perform to increase the pressure of the hydrogen? The polytropic exponent N is critical for accurately modeling real-world processes. In ideal cases, we can assume N is equal to 1 for isothermal processes, where the temperature remains constant. N is equal to gamma for adiabatic processes, where no heat is exchanged with the surroundings. However, in most real-world applications, the system is influenced by both heat and work interactions, making N fall between 1 and gamma. This reflects the fact that some heat is transferred to the surroundings and that the process is not fully adiabatic. Compressors and expanders typically operate under conditions that deviate from ideal thermodynamic models. For instance, in hydrogen storage and fuel cell systems, the heat generated by compression is often transferred to the surroundings, and work is done on the gas to change its pressure. The polytropic approach helps engineers design more efficient systems by allowing them to adjust the value of En to reflect real operating conditions. In practice, we very rarely see ideal isothermal or adiabatic processes, and the polytropic process provides a flexible tool for modeling these intermediate states. At this point, it's time for another interactive task. The question is, can you calculate the final pressure P2 using the polytropic equation and the work done by the compressor? Being able to calculate these values is important for a great many reasons. When dealing with a system involving tank storage, to give just one example, calculating the final pressure is a necessary step in ensuring safety. If the storage tank is not rated for the calculated final pressure, it is clear that a dangerous situation could arise. Less dramatically, having a value for work done allows engineers to develop an accurate picture of the efficiency of the compression process, which can help them identify opportunities for system improvement. In the previous task, we saw that making relatively small changes to each of the input values has produced quite different results. In the next task, you will have an opportunity to see the effect of changing just one value at a time. In the previous task, we saw that making relatively small changes to each of the input values has produced quite different results. In the next task, you will have an opportunity to see the effect of changing just one value at a time. Pay close attention. You will see what happens when different inputs are changed, and then there will be a very small test. First, let's change the initial volume and see what happens as we increase and decrease the value. Now, we can reset that and move on to initial pressure. Let's start by decreasing the value and then pushing it right up. What about final volume? Let's reduce it and then increase it. Now for the test. The polytropic exponent is also a value that can change. This is one reason why it is useful. Not all hydrogen systems are identical, and all must operate in scenarios where different conditions apply. Even small changes can produce quite different results. It is always important to remember that real-world operations do not always follow a standard script, in which we only ever have to calculate the final pressure or work done. It may be that these values are known or measurable, but that some other value is not. In such cases, we can rearrange the polytropic equation to find these other values. In the next task, this is what you will do. We're nearly done, but before we finish, we will do one final task, which is designed to emphasize the importance of the polytropic exponent n. It is also something that should be a little easier now that you are familiar with the equation and the way it works. This exercise, you've explored the concept of the polytropic process and seen how the polytropic exponent can be used for thermodynamic modeling. By understanding the versatility of the polytropic process and applying it to hydrogen systems, you should be better equipped to work with real-world technologies, including compressors and storage systems. These insights are valuable for designing and operating efficient energy systems, especially when dealing with hydrogen, where both heat and work interactions play significant roles, and where pressure, volume, and temperature are always key considerations.